Yes, I hope you're doing well. Teacher Dennis Monday back with the physics lesson for senior two. Yeah, so I need to remind you that you need to subscribe to this channel, Dennis Monday Uganda, never to miss any of the lessons that I'll be uploading here. Yes, it's called Dennis Monday Uganda. That's the name of the channel on YouTube. Please subscribe to the channel and like the videos there. You can share them with your friends. Okay, we are continuing with our topic of pressure, and this for senior two physics. This is lesson 3. It's entitled pressure in fluids. So this is the first part A. Part A. Pressure in fluids. So let's first understand what is a fluid. So a fluid is a substance which can flow. From the verb flow, we get the noun fluid. And in other words, the term fluids refers to liquids and gases. So the term fluids generally means liquids and gases. Some people think that only liquids are fluids, but you have to understand that even gases are also fluids. So that means that if we need to explore everything concerning fluids, pressure in fluids, we shall have to look at pressure in gases and also pressure in liquids. Okay, now pressure in liquids, that's what we're going to start with. And for this short video, we're going to explore actually the first part of the pressure in liquids, and the content is here. We are going to derive the formula for the pressure in fluids, and after that we shall look at the factors which affect pressure in liquids, and we do investigations on those factors which affect liquid pressure. So let's start with the derivation of that formula. When a liquid is poured in a container, we all know that the liquid takes up the shape of the container, and the liquid will exert a pressure at the bottom of the container. So let a liquid of density rho be poured into a cylinder of base area A to a height h. So here we have a cylinder, and the cross-sectional area is A, the base area is A, and then we are pouring in a liquid, maybe water, to a depth, sorry, or to a height h, Okay, now we want to determine the pressure that this liquid will exert at the bottom of the container. Understand that to get the pressure from what we learned in the first 2 lessons, we said the pressure is the force acting normally per unit area. So you get the force divided by the area to get the pressure. So it means that we have to get the force which is acting on the base. But remember, the force is the weight. That means we need to calculate the weight of this liquid here. But to get the weight, we have to first have the mass, and we have to have the volume. Now remember, actually you have to have the mass times the acceleration due to gravity to get the weight. So we have a cross-sectional area here, A, and the height is h. Or in other words, the depth from the liquid surface to the bottom, that is h. So the mass of the liquid, you know how to get mass. It is volume times density, and the volume is simply cross-sectional area times the height. So you're going to get AH, that is the volume. AH is the volume, then times rho, which is the density. That gives us the mass. In other words, the mass is AH rho. Please note that. If we have the mass, therefore, we can simply pick the weight. We know that weight equals to mg. So for us to get the weight, we multiply the mass we've obtained times acceleration due to gravity. So in other words, the weight is now AH rho g. Now, once we have the weight, it means that we have the force which is acting on the base. So let's return now and get the pressure. So the pressure is force over area, you know that. Our force is the weight divided by the area, and that gives us the AH rho g, that is the weight, divided by our area. Which area? is actually A, is actually A. So we are going to end up with the pressure equals to H rho G. Pressure equals to H rho G. Because of course here you realize that we have cancelled out. We have cancelled out the A up goes cancels with this A here. So we end up with H rho G as the one left, as the one that is left. That we are moving, that we are just transplanting. These ones have gone. So we have this, that pressure equals to H rho G. All right, all right. Now, if that is true, I want us to proceed. I want us to proceed and okay, I've put that in a box. Understand that H is the depth below the liquid surface, rho is the density of the liquid, and G is the acceleration due to gravity. And these are the three factors that affect the pressure in liquids. Please note that this formula applies to both liquids and gases. Understand that this formula is not just strictly for liquids, it's general. It's a generic formula. Let's look at an example here. I've got to remove this annotation. Let's look at this example. So water is poured in a calibrated cylindrical container shown in the figure below. The density of water is 1,000 kilograms per cubic meter. Determine the pressure due to the water column at the point marked B. So we are starting with a point marked B. There is a point B down here. You can see it. A point B at the 0 centimeter mark. So we want to determine the pressure. Of course, if you can remember, the formula we've just written is pressure equals to H, we get H rho and then G. So we have H rho G, H rho G. So now, what is the depth? The depth is measured from the liquid surface. Please never make a mistake of doing the height. We look at the depth. From the liquid surface down to the bottom, the liquid surface, you see it's around, oh, sorry about that. The liquid surface is around here. If you can check clearly, around there, 100 at the 110 centimeter mark. So the depth at that point, therefore, is going to be 110 because you get 110 and you subtract from and 1. All you need to understand is the depth. The depth is going to be 110 centimeters. We are going to do the calculations together. Then in Roman 2, what is the depth? From the 30 centimeter mark. From the 30 centimeter mark, there is that depth there. And you can clearly see that that depth is 110 minus 30, which gives you 80. So we have 80 centimeters. 80 centimeters. So because it is 80 centimeters, let me quote here and say H is 80 centimeters. 80 centimeters for Roman 2. And for Roman 3, we can clearly see that our H is going to be 110. 110 is the mark. The 110, that is a reading where the surface of the liquid is. So we are going to have 110 minus 60, giving us 15 centimeters. Of course, you have to remember that before you use this depth, you must convert them from centimeters to meters. You have to convert them from centimeters to meters. So in other words, we are going to have that Roman 1. Actually, let me just display the full working displayed. Okay, for Roman 1, the depth is 110 centimeters, which if you convert to meters by dividing by 100, it will give you 1.1. And then now pressure is going to be H rho G. formula, the H is 1.1 times 1,000, which is the density of water, times G, which is the value, which is 10. So we're going to end up with 11,000 pascals for Roman 1. Then for Roman 2, at the depth C, at C, the depth H is 80 centimeters, which is 0.8. We've already done that, 0.8. And if you substitute in the formula pressure equals to H rho G, you're going to get the depth of 0.8 times 1,000 times 10, giving us 800 pascals at point C. And then if you take it further and you look at Roman 3, at D, the depth, we got 50. Yes, we got 50 centimeters, which is the same as 0.5 meters. And if you substitute in our formula, P equals to H rho G, we're going to end up with 0.5 times 1,000 times 10, giving us 5,000 pascals. 5,000 pascals. Now, number two. Yeah, this one's actually, let me first take back. You can take a screenshot, but you can always pause the video and then you write if you're writing. Number 2 says the pressure of water on a stone at the bottom of a sea is 15 million pascals. Determine the depth of the sea given that the density of water is 1,023.6 kilograms per cubic meter. Let's have an answer. It's just direct. We substitute in the formula P is equal to H rho G. The pressure has been given. Check this out. The pressure is given and it's just right here. The pressure has been given as 15 million. If they don't give you 15 million, someone can say 15 megapascals. Megapascals. A capital M means million. 1 ma is 1 M. 1 M is 1 million. So 15 megapascals, that's what was given here. If you ever find a kilo, small k, it means 1,000. So the pressure is given, it's right here. This is the pressure. And then, you know, they're asking for the depth, so we don't know the depth. We know the density of seawater, it has been given as 1023.6, and this one is ever 10 on Earth. We take 10 for, not all the values, by the way, for all level we shall keep taking 10. Okay. If you substitute, of course, you're going to end up with 15 million equals to 1023.6 H. Divide both sides by 1023.6. You end up with H equals to 1,465.416 meters. So in other words, the depth of the sea is 1,465.416 meters. Wow. By the way, you have to know that the sea is very deep. It is kilometers deep. Kilometers deep. Can you imagine? Kilometers deep. Okay. Okay. I want us to go to now number 3. Number 3. I need to stop this animation. Okay, the annotation is gone. Number 3 says, given that the atmospheric pressure is given as 10,000. No, it's 103,360 pascals at sea level. What is the total pressure at the bottom of the sea in question 2 above? What is the total pressure? Now, someone may not know. Let me show you something here. If you have this as the ocean, for example, if this is our ocean, and this line here, this is representing the surface. Here we have the surface, the sea level here. Now, did you know that from sea level to the bottom, there are kilometers? If you have this from sea level to the bottom, that's some good depth. Let me just represent here with some mark. Do some marking here. This is our stone that they are talking about. And we are told that we have calculated, I think in the first case, we were told that the pressure that is being exerted on this stone due to the water pressure, but it is because of the water column. The pressure due to the water column was the 15 megapascals. 15, then you put million. 15 million pascals. 15 million pascals exerted there. Now, remember at sea level, there is atmospheric pressure. This is what I wanted you to know. Let me note it even in another color, green. At sea level, there is atmospheric pressure acting. The pressure acting due to the weight of the air exerted on the earth. Atmospheric pressure is acting at sea level. And its value was given as 10,3360. 3360 pascals. Now, it means that since these two pressures, you can see they are okay. Pressure is a scalar quantity because it doesn't have a particular direction in which it acts. But realize that these two, we are saying they are being exerted downwards. So in other words, the pressure at the bottom is going to be a sum of the two because they are all facing in the same direction here. So you have this pressure plus this one here. So those two pressures, when you combine, will give you the pressure at the bottom of the sea, or the total pressure that is acting on the stone. The 15 megapascals, 15 million the 15 megapascals or the 15 million pascals, for them, they are acting due to the water. That is the pressure acting due to the water, not atmospheric pressure. At that point was, for that calculation, was ignored. For that value, it's not considered. But if you want to get the total pressure, then add the two pressures. Please do not forget that. All right. Let's go. Okay. Remember that pressure in solids, remember these two conditions or factors on which the pressure in solids depends. So the pressure in solids depends on two factors, namely the area of contact and the normal force. They all come from the formula which we all remember very well, that pressure equals to force over area. So these are the two factors, the normal force and the area of contact. Those are the two factors which affect pressure in solids. Now, the factors which affect pressure in liquids are similarly obtained from the very formula that we wrote a few minutes ago. Pressure equals to H rho G. So what is the H? That's the depth. What's the rho? That's the density. G is the acceleration due to gravity. So in other words, the factors which affect pressure in liquids are density of the liquid, depth of the liquid, and acceleration due to gravity. Now, our last, what is required to for us to finish the objectives of this lesson is to investigate those factors. We're going to look at just one simple concept, and then we close it up here. Pressure in liquids is independent of the cross-sectional area and the shape of the container. This is a very important statement, and we are going to just show that, demonstrate that very soon. Roman 2 says, the pressure applied on the surface of an enclosed fluid is transmitted equally throughout the fluid in all directions. Therefore, pressure is a scalar quantity since it is transmitted equally in all directions in the fluid, and there is no single direction in a fluid along which the pressure acts. two important notes. We're going to emphasize on note number 1 by doing an experiment to show that pressure in liquids is independent of the cross-sectional area and the shape of the container. So this experiment is very simple. We pour water into communicating tubes. What we mean by communicating tubes, they are like this. So we have tubes here, we can label 1, 2, 3, 4, 5. There are 5 tubes. You can realize that they are connected, so they are called the communicating tubes. And they have different shapes and different cross-sectional areas. So once water is poured in them, we observe to which level does the water rise in each of those tubes. So communicating tubes refer to a set of tubes with different shapes and different cross-sectional areas, but it must be connected together. Here we are. We have communicating tubes here, connected properly. Let's fill it with water. When you fill it with water, you see what happens? The water rises to the same level. Look at this, the same level in all of those tubes, the same horizontal level. No matter the cross-sectional area, no matter the shape, water rises to the same level. So that's how the communicating tubes look like. If you want to see the real picture, that's how they look like in normal life. The other one is just a sketch of these very ones. All right. So remember that water flows and settles at the same level in all tubes. And this shows that the liquid or water finds its own level, and that pressure is the same as the same level, is the same at the same level regardless of the shape or the cross-sectional area. So a liquid finds its own level, and pressure is the same at the same level regardless of the shape or cross-sectional area of the container. So in other words, remember that cross-sectional area and shape of a container do not affect pressure in liquids. All right, therefore pressure in liquids is independent of the shape and the area of the container. Wow. Thanks so much for watching. Thank you so much for watching. And subscribe to the YouTube channel, Dennis Monday Uganda. And I ask you kindly to enroll for the most affordable online coaching lessons. You can enroll, please. For details, contact me. We have physics, chemistry, biology, math, English, and so on for S1, S2, S3, S4, S5, and S6. And the contact is right here of the person who will help you, and that's me, myself. Thank you very much. Let me wish you the best of the rest of the day. Bye-bye.